This is part 2 of the Bessel's equation of order 1. In part 1, we found the solution using the Frobenius method, and we found one solution only, which is called the Bessel function of the first kind of order 1. And being a solution means that it satisfies this relation. Now, before I try to solve for the second solution, I have to say that the approach that I'm trying to do in this video is not the common one because it's not the most efficient one. Most books approach it this way, and I will make another video for this other method. And if your goal is just to understand what Bessel function of the second kind is, then I advise you not to watch this video, but instead watch that video. But I'm still trying to do it this way because I want to show how the logarithmic singularity solution is obtained and how that relates to the usual Bessel function of the second kind. Okay, well, this is the Bessel function of order nu, and its initial equation has the solution r equals to plus or minus nu. And because it has plus or minus nu, there's one solution like this, and there's the other solution, j of negative nu. It has this gamma function in there, and I have a video on gamma function, so if you don't know what gamma function is, please watch that as well. And the nice thing is that if nu and negative nu are not integers, then these two are linearly dependent. Now, generic Forbinius theory says that if two solutions of the initial equations, if they differ by an integer, then the second solution may not be of the Frobenius type, Frobenius form x to the r sigma a n x to the n. It may have a logarithmic singularity, and that will need a different approach, which I'm about to do. So you can see that if nu is an integer or a half integer, then such a thing happens. Now, luckily, when nu is half integer, the logarithmic singularity doesn't appear, and they both are expressed this way, with r being positive nu and negative nu. So this one and j negative nu, which is just the same thing with nu replaced by negative nu, those are two linearly independent solutions, and we can just happily go about using that as the solution. However, if the nu is not, if the nu is indeed an integer, then what happens is that there's a fact that gamma of negative n, where n is a positive integer, this is undefined. It goes to infinity or negative infinity. And because of that 1 over gamma of negative n, it's like 1 over infinity, so this becomes 0. And that means the first few terms of j negative nu, when this thing is negative, it's not going to show up, it will vanish. And then once it starts to show up some terms, some of the non-zero terms show up, they happen to be exactly like this one or negative of this term. So you end up having the following identity, that j nu is equal to negative 1 to the nu of j negative nu if nu is an integer. And if one is a multiple of the other, that clearly means that the two functions are not linearly independent. That means that you have to try to find the second solution in a totally different way. Okay, so how do you go about that? The standard way that people use is to define the Bessel function of the second kind this way. And if you look at this, because cosine nu pi and sine nu pi are constants, you can view this as like some constant times j nu plus some constant times j negative nu, where the first constant is really cosine nu pi over sine nu pi, and the second constant is negative 1 over sine nu pi. And if these are well defined, then indeed this will be a solution of the Bessel's equation because it's a linear combination of two solutions. And moreover, if nu is not an integer, then and if C2 is not 0, which is exactly the case, 1 over sine nu can never be 0, in that case, this will clearly be linearly independent from this because of this linearly independent term. And that means this will be a good solution. This can work as the second solution to give you the full general solution of this second order differential equation. But what about when nu is an integer? In that case, we can no longer say that this is linearly independent, but somehow if you take limit nu going to 1, then these, although they are these functions are going like it goes like, if it's an integer, then it goes like negative 1 over sine of 0, which is the denominator becomes 0. The overall, the top becomes this actually becomes 0 as well as you send nu to an integer. And actually that's because sine nu pi, or nu is an integer, that's exactly this one. So this actually guarantees that the type is 0. So because it's 0 over 0 type, you can use the L'Hopital's, and when you differentiate using the L'Hopital's, you end up seeing these logarithmic terms appearing. And that's how you get the second solution. And because that has a logarithmic singularity, then you know that that must be linearly independent from the first one, and you found all the solutions. So that's the brief sketch of what happens in this other approach, and I will make a video for that. So please watch that instead if your goal is to just understand what Bessel function of second kind is. Okay, so I think I spent too much time in the introduction. Now let's try to actually solve this. Now, because this one has the industrial equation solutions as +1 and -1, the positive one case gave us this J1x, the Bessel function of the first kind of order 1. The second solution, Frobenius suggests this, but because 1 and -1, they differ by a constant, sometimes this fails. And indeed, if you try to plug this in and solve, you'll see that all of the ANs must be 0, and it fails to give any meaningful solution. And that's why in that case, Frobenius says, just multiply the first solution that you got times the logarithmic singularity, log function, and then you multiply it by some constant that has to be determined later. Okay, so what we want to do is we want to work with this. Now, in order to figure out what happens when you plug this in here, because the computation is quite involved, let me rename this part as u of x. So u of x is really just a shorthand for this summation, so it's easier to track what's happening. Now, if you now plug this into here, you will need to, in order to plug in, you'll need to find the first and second derivative, and of course when you differentiate you have to use the product rule, so I get all these product rules. And then you have to remember that when we said that J1 is a solution to this differential equation, it means that it satisfies this relationship, which we'll be using later. Okay. Now we're going to plug in everything into the above. Let's see what happens. It's going to be, this will be x squared times the second derivative, edit most terms, x times the first derivative, and x squared minus 1 times y itself. Then if you multiply the x squared inside, you get, if you just look at these three, so x squared times this, x squared minus 1 times this, then you can see that you end up with this, I forgot this, times c times ln of x. So all of these will have c times ln of x multiplied, so I can factor that out. And if you factor that out, this is very this is very familiar, right? It was exactly the relationship we talked about. It was this relationship which gives you 0. So because it's 0, this will now become 0. And with that out of the way, now we have to simplify this. So let's see what this can be simplified to. Okay, so what we want to do is we want to multiply the x squareds and write it like this. Multiply the x's, write it like this, and then x squared minus 1, ux will be this. Now, if you look at this term and this term, oh, they're exactly the same with opposite signs, so I can cancel them. And after canceling them, we have a beautiful equation which seems very much like our Bessel's equation of order 1, except that you have this extra. And it's actually this extra term that's going to help us, because this will prevent all of the coefficient of u of x from being 0. Okay, so this is exactly what we want. Okay, so this is the equation that we have to try to solve. All right, so let's investigate this one by one. First, what is this 2c j1 prime x times x? j1, as I indicated earlier and I found in part 1, is this function. And if you differentiate using just the power rule, 2n plus 1 comes down, and you subtract 1, and then because of the chain rule, the derivative of x over 2 becomes 1 over 2. And then you multiply 2c j1 to this thing, 2 and 1/2 will cancel, right? 2 and 1/2 will cancel. You still have c and x multiplied, so that's c and x. And then because x is x to the first power, and you can rewrite this as x to the 2n times 2 to the negative 2n, you can multiply these two to make it look like x to the 2n plus 1 times 2 to the negative 2n. Okay, now to understand what's really happening, it's quite nice to write out what this summation means. So this summation means when n is 0, you have 0 factorial, which is 1, and 1 factorial, which is again 1. When you plug in 0, this is just 1, that's 1. This is 2 to the 0th power, so that's just 1. So everything's 1 except, yeah, even this is 1. So you just get cx. You just get cx if you write down the very first term. And then when you plug in n equals to 1, you get 1 factorial times 2 factorial, which is 2, but 2 to the negative 2, that's 1/4. 1/4 times 1/2 will give you 1/8. And then actually there should be a 3 there, right? When n is 1, there should be a 3. Okay, I think I forgot these 1, and then when it's 2, there should be a 5. When there is 3, there should be a 7. Okay. All right. But anyways, you have these, and you can see that once you write them out, n doesn't play any role at all. So you're really free to write it as k. And the reason I want to do this is because for u, we had the equation of u written as x to the r, or x to the negative 1, sigma a n x to the n, and we're using n. And if I use both as n, then we're going to get confused. So I just want to use k for this. All right, so that's what happens. On the other hand, let's go back to u. U of x is an times x to the n minus 1 if you bring this x to the negative 1 inside. And also, when you have terms like this, it's better to multiply them out. And what we want to do is we want to find the first and second derivative and plug them into this equation. And if you plug them into the equation, this is what you get. You have x squared times n minus 1 n minus 2 a n x to the n minus 3. X times n minus 1 a n x to the n minus 2, x squared a n x to the n minus 1, a n x to the n minus 1. Now hopefully you've seen enough examples of Frobenius method that you're following me. I'm going rather fast here, so if you have trouble following this, rather than stopping the video and watching it, I would recommend you to watch my other videos where I explain the Frobenius method. Okay, so once you have these plugged in, then you can bring the x squared inside to make this as x to the n minus 1. X goes in, again x to the n minus 1. X squared goes in, that's 2 plus n minus 1, that will be n plus 1, right? And then the last one is just n minus 1. And what we see is that these three all have x to the n minus 1 in there, so that's good, but this one is different. So what we want to do is we want to shift the indices, okay? All right, so how do we shift the indices? Oh, well, let me try to explain it here. What you want to do is, in order for n plus 1 to become n minus 1, what you need to do is replace n by n minus 2. If you do that, then n minus 2 plus 1 will become n plus 1, right? N plus 1 will be, sorry, n minus 2 plus 1 will be n minus 1, right? N plus 1 will be n minus 1. This then will become n minus 2. And this n equals to 0 will become n minus 2 equals to 0, which is equal to n equals to 2. So the resulting summation is sigma n equals to 2 to infinity a of n minus 2 x to the n minus 1. Okay, so, and you can really see that these two sigma notations produce the same terms by just plugging in these things, just like how I showed you with the derivative of the Bessel function a moment ago. Just write out the terms and you'll see that these are the same thing. Okay, so you have that, and we are happy because now everything is in terms of n minus 1, except this one. We have to be careful. But here's what we have. Let's look at the x to the negative 1 term. That's the case when n is equal to 0, right? When n is 0, it produces x to the negative 1. However, because this summation starts at n equals to 2, this one is silent. It doesn't produce anything at all. When you're looking for x to the negative 1 term, you're only looking at the first, second, and the fourth sigmas. And just by plugging in n equals to 0, you get these terms produced. And if you actually write them, you see that the terms produced is 2a0 x to the negative 1 minus a0 x to the negative 1 minus a0 x to the negative 1, and that just gives you 0 because it's 2 minus 1 minus 1. So this is automatically satisfied. Automatically satisfied. And indeed, that's what happens if you use the correct index. If this is the very first one is not 0, that means you made a mistake in finding the initial equation. All right, now for x to the 0th term, that corresponds to when n is equal to 1. Again, the third sigma doesn't produce any terms, only the first, second, and fourth produces. And if you see them, you see that because the first two are at 0 anyways, the equation that you get is that a1 x to 0 equals to 0, which means you're forced to have a1 equals to 0, because x to 0 is 1, so you're forced to have a1 as 0. Okay, and then if you look at the x to the first term, n is equal to 2. Now all of these terms start producing that. Not only that, remember that the very first term of this started with cx, right? So we're going to use that. Cx is the term produced by this. Whereas if I plug in n equals to 2, this will be 0, this will be 1, this will be this, and then we have a2 x, but these two cancel, right? And we have actually cx plus a0x equal to 0. And since this has to be true for any x inside some interval, this leads us to say that c has to be negative a0. And that's a very good achievement because now we know what to put for the c. C value has to be equals to negative a0. This should be written somewhere. Please remember this because we will be needing this later, okay? Well, actually, we will continue with this solution with c being replaced by negative a0, but we will use this again in some later period. Okay, so these are our conclusions that C must be negative a0 and a1 should be 0. And if you assume that a1 is 0, then the x to the negative 1 and x to the 0th power terms, those disappear anyways. So really, these things that starts from 0 can be just considered to start at 2, because the first two cases when n is 0 and n is equal to 1, they produce null results. So we can do that. We can replace the n equal to 0 by n equals to 2. And that's nice because now that they have the exact same sigmas, I can put them into a single notation, single sigma. So I put them into a single sigma just like this, and we will simplify it just by first pulling the x to the n minus 1 out and combining the an's together. And the result is that you get n squared minus 2n an plus an minus 2 times this equal to 0 with this 2c j1 prime x times x. Okay, now we can further simplify this by factoring the n out. And remember, we calculated this. 2c j1 prime x times x is this. And because c is equal to a0, we are going to rewrite it in this format. And because this is using n, I don't want to get confused with it, so we'll be using k instead, just like how I explained before. And then plugging this into this, replacing this stuff, the first term, will give you the following equation. Okay. And sadly, it's not possible to somehow shift this or shift that to combine this into a single sigma, because this one is producing only x to the odd power, whereas this one produces both x to the even power and odd powers. So there's no way to combine that into a single sigma. So for a while, let's just leave it like this and just look at what powers of x it produces and see what equations you get. So first, x, the first term, that's when k is 0 and n is 2, will give you the following. And that's a meaningful equation. We'll see. Actually, let's see. This is one. Oh, so this one just has negative a0. Actually, it should be x1 should be factored out. Negative a0 plus a0. So that's just 0. So this is automatically true. And this actually was done before. We already made x the first term, first power 0, so that's already 0. How about x squared term? That's the case when this one only produces odd terms, so x to the even power is not produced from the first sigma. But in the second one, that corresponds to when n is 3. But remember that a1 was 0, right? And therefore, if the second power produces this and a1 is 0, then you're forced to have a3 as 0, right? Okay, now let's go further. X to the third power term will correspond to when k is 1 and n is equal to 4. You can write down some equation. X to the fourth power, again, no k value will give you anything, but n equals to 5 will give you this. And because a3 is equal to 0, a5 is again equal to 0. And then you can proceed by plugging in further values and you get this. But as you go, you realize something. All the odd terms will be 0. So if you know that all the odd terms are 0, then that means we can only consider this when this is even, right? So when is n minus 1 even? Well, that's when n is odd, right? So that's something you can always do. You can replace n by 2k plus 2 because oh, sorry, for n minus 1 to be odd, you need n to be even, right? And certainly 2k plus 2 is even, and I chose 2k plus 2 rather than 2k because 2k plus 2, when plugged in, it will give you exactly the same extra 2k plus 1 as this one. And that will enable us to put these two into a single sigma. Okay, so that's what we do. Okay, so we replace n by 2k plus 2 and rewrite this, and this is usually not possible, but it's only possible because n can only be even numbers. The odd terms are all 0, so it's meaningless. Okay, so great. So now we have the two sigmas look very similar. And they're looking very similar, so I can put them into single sigma. And when you put them into single sigma, then you get a relationship just like this, which is a recurrence relation, right? Okay, so now let's happily start plugging in the values for k. So when k is equal to 1, you get this. That's k equals to 1. And when k is equal to 2, you get this. But you start noticing something. See, this equation you can solve for a4, and a4 will be something times a2 plus something times a0. a6 will be solved by a6 will be something times a4, but because a4 is something times a2 plus a0, again, it will be something times a2 plus something times a0. And at first, you're a little confused or nervous because usually when you did the Frobenius method with single, with the usual method, you just get single free variable, okay? But this actually has two free variables. So you kind of hesitate for a bit, and you start questioning why that's true. But the answer is simple. Because we're trying to solve a second-order differential equation, and second-order differential equation can have at most two free variables. Having two free variables means that you've already, just continuing this will actually give you all the solutions, okay? And the second one, a2, will just create some multiple of the Bessel functions, okay? And because and the reason I say that is because if you only consider the ones that contain a2, that's not going to contain any of the logarithmic singularity, right? And because of that, it should be some multiple of j1. Okay. So what does that mean? That means since we already have j1, we can just decide to have, so I wrote here, it shows that indeed a2 is a coefficient of xn. So what I want to say is that since I already have j1, you can just make a2 any arbitrary value, and for example, we can make a2 as 0. And if you make a2 as 0, that's the same thing as solving it honestly with arbitrary a2, and then subtracting a2 times j1 from the solution. But actually what happened was that I tried to solve this with a2 equal to 0. At this point, I thought, okay, so let's just make a2 as 0, and then I proceeded to solve this recurrence relation. And what happened was that the recurrence relation becomes extremely hard, and I could not find any pattern at all. So because of that failure, after trying so many things in one day, I looked for some other books, and I realized that other books, they choose a2 to be 1/4 of a0, which is possible. And actually what happens is that the moment you choose this, then the ANs become something manageable, and we start seeing some pattern, okay? So and I feel like this actually came from reverse engineering the other solution that I talked about in the beginning, the Bessel function of the second kind. I can't be sure, but it seems like that's what they did. Okay, so we take a2 to be 1/4 of a0, and what I do is I just now solve this recurrence relation for ak plus 2, and once you have it solved, then you start plugging in values like before. So when k is 1, since we have a2 as 1/4 of a0, if we replace a2 by 1/4 of a0, then factoring the a0 out, and then furthermore factoring the -1 to the first power and 2 to the fourth power 2 factorial out, then the remaining thing is 1 plus 3 over 2. That's what you get, 1 from the first one. And this one, when k is equal to 1, you get 3 here and then 2 here. So this over this gives you 3 over 2. But 3 over 2 is 1 plus 1/2. And this seems like outrageous. How could anybody think of that? But again, if you start from the known solution, the second kind of the Bessel function, then you can see that they contain harmonic terms, so you can very much see that these should be the pattern. Okay. Now you plug in k equals to 2, plug in 2 here, you get 1 over 2 squared 2 plus 1, 2, and then you plug in k equals to 2 here as well. And again, if you look at this 5 over 2, that's what happens. Actually 5 over 6. Right, 3 times 2 is 5 over 6. Notice that 5 over 6 is same thing as 5 over 6 is 1/2 plus 1/3. So if you rewrite 5 over 6 as 1/2 plus 1/3, then you end up putting the 1/2 added to this first one and 1/3 added to the second one. So it seems like we're onto something, and indeed what's happening is that if you put this thing, which seems to be the provider of the pattern, you can do a partial fraction expansion. If you don't know what partial fraction expansion, just see that this is indeed 1 over k plus 1 over k plus 1. See, if you put these two fractions together by common denominators, you get k plus 1 over here, k there, and k plus 1 times k will be the denominator, and k plus 1 plus k gives you indeed 2k plus 1, right? So partial fraction expansion will give you this, and once you write it that way, then it becomes clear that every time you put something higher, this one will reproduce the previous term with some multiple, and this will give you this extra 1 over k and 1 over k plus 1 to get further terms, okay? And these numbers are called harmonic numbers. And this we can call it h of 3, and this we can call it h of 4. And once you have named them like that, then you can see that this 8 is 2 times 4. So or 2 times 3 plus 2, you can see that for a2k plus 2, the general pattern is this, where hk and hk plus 1 are harmonic numbers. Okay, so that's great, because now I figured out what ak plus 2 is for any k, which means now I can go back and plug in all the known things and get the solution. So let's do that. So we had c equals to negative a0, and originally we call this as u of x, right? But we also know that the odd ones disappear, and only the even terms they're produced. And then what you get is when you replace a2k plus 2 by what we just figured out, and I pulled out the a0 over x separately, then you get this as the solution. So that's like almost the end, okay? So what we can do is we have this result, which is the other part. As you can see, we do find a solution with the logarithmic singularity. And if you want to ask what's the relationship between this solution with the traditional Bessel function of the second kind, is that you can rewrite this with a0 being negative 2 over pi, and then you add this much times j1. That creates the Bessel function of the second kind. And here this gamma, this mysterious number, lowercase gamma, is what's called the Euler-Mastroianni constant, and its definition is this limit. And that's it. Oh, this was such a challenge. Thank you for watching.